right? But at any moment, at not any moment, I mean, at the output of after any unit, if you just observe the top signal and the bottom signal, they will be exactly time reversed. 时间整个颠倒过来就是。And I'm not sure does that sound surprising. There's this time reversal feature. Maybe I put it in one equation, okay? There's a property which might not be obvious to you, but we can prove it, of course. But this is somewhat surprising property that for any I, let me say 0, for any I basically, and for any I, actually, the I of z is exactly the time reversal of a I of z, and the mathematical expression is a of 1 divided by z, ai, with z to the minus I. So that's a somewhat surprising property. There is a symmetry. Once we have this topology and we propagate the input into the network, it turns out that at any place, if you look at observe the top signal and bottom signal, they are going to be exactly time reversed. For example, let's say if A3 of z is, I'm just going to randomly assign numbers, okay? I'm just going to randomly assign if A3 of z is 1 plus 0.2 z inverse minus 0.3 z to the second power plus 8 z to the third power. If this is A3 of z, then I'm going to show you by applying this property, which we're going to prove next. Assuming that this property is true, assuming that this property holds, then what is B3 of z? That's my question I want to invite you to answer together. Okay? So if A3 of z is that, then A3 of 1 divided by z, what is that? It should be 1 plus 0.2 z, not the inverse, minus 0.3 z to the second power, at least as far as the kind of symbol is concerned. Okay? At least symbolically, A3 of 1 divided by z, if you just simply substitute 1 divided by z into the polynomial. Any objection? Any objection? Objection. Any objection? Right? This is as straightforward as it is by definition. Therefore, if we just further multiply that with z to the minus I power, I being 3. Therefore, z to the minus 3 third power, a superscript 3 of 1 divided by z should be quite straightforward. Z to the minus third power plus 0.2, z to the minus second power minus 0.3, z to the minus 1 power plus 8, Okay? And we claim that this is exactly B3 of z. So that is to say, if A3 of z corresponds to a signal that is A3 of n, if A superscript 3 of n is 1 plus 0.2 minus 0.3 and 8. If this is A3 of n, then I'm saying that B3 of n is exactly the time reversal of A3 of n, and there, such is the symmetry. And that's one unique property of lattice structure, of the lattice structure we are looking at right now. So I'm suggesting that since now, I hope I've convinced you that this relation indeed describes time reversal. Okay, this relation describes time reversal. This is a time reversal formula, you know. So I'm saying that, so we're saying that now, B3 of n, B3 of n should be 8 for the first sample, and minus 0.3 for the second sample, and plus 0.2 for the third sample, and 1 for the fourth sample. There are 4 samples in this signal. Exactly the time reversal of a superscript of n. And that's, this relation is nicely described by this formula. Any question here? Any question here? So I think this property is somewhat surprising. It could be somewhat surprising. How on earth? What's the reason why this should happen? Okay. Now, if we just simply accept that this property is true, we can prove it. It's not hard to prove it. But for now, if we accept that this property is true, then how can we refine our algorithms so that the computation becomes more efficient? Let me say the question again. Then knowing this property, how do we refine this algorithm so that it becomes computationally more efficient? How do we improve the computational efficiency? And the answer should be pretty straightforward. The answer I'm going to suggest, okay? Because in this algorithm, where's the algorithm? Oh, the algorithm right here. So in this algorithm, the second step is to do equation 1a and equation 1b. But now we know b is simply a in reverse, right? So actually you don't need to do 1b anymore. You just simply reverse a, and you can propagate to the next video. So that kind of a good property to know about. All right, so now I'm going to just write down this final algorithm suggested by the textbook. Algorithm 2, right? So now, so this is just simply copying the algorithm from the textbook. Okay, so, oh, by the way, I realized that this part is not in second edition of the textbook. It's only in the third edition, which is our required textbook. So if you have a copy of the second edition, please feel free to photocopy this section from the third edition. Okay? I think it's fine. It does not violate any, because you are just copying this section, all right? Okay? So just make sure that you know that this is in the text, only in the third edition textbook, okay? Not in the second edition. But here's the algorithm. Given, still we are interested for the same question. Given k1, 2k, and these lattice coefficients, and then there's a double loop in this algorithm. I'm going to share with you. Double loop for I equal to 1, 2, all the way to n. And inside, we have an if statement. If I is greater than 1, then for J, we have a nested loop. J is going to start from 1 to I minus 1. Okay? So that's the structure. We have a double for loop, nested for loop. So we are going to define this variable alpha. Alpha I superscript I for every j let me just write it down first, and then I'll explain. Is alpha I minus 1 j minus k I using the lattice coefficient alpha I minus 1, this is I minus j. And then we'll end the j, the for j. And then for every I, since we add one more assignment, I sub I, let it equal to ki. And then we close the for loop for index I. Okay? And then in the end, let's define, actually our impulse response is going to be defined as 1 minus summation from j from 1 to I. Oh, by the way, it should be pretty clear this j is not the square root of minus 1. Okay, j is simply j in units. Right? We're not doing any complex variable. Okay? Alpha superscript I subscript j v to the, should be minus j. So that's an algorithm for you to calculate the impulse response of this system. Given the lattice coefficients. I'll let you contemplate upon this algorithm for a few seconds, and then I'll jump in to explain why such is the case. Actually, in coming up with this very concise expression, it's a very concise expression. Okay, so let me just point out, all right? So here, there's this alpha variable, see? This relation really is exactly the same thing as equation 1a. Equation 1a. Equation 1a says that this a superscript I of z. A superscript I of z is a superscript I minus 1z minus something. Okay? So this term really corresponds to a superscript I of z. I say roughly it corresponds to that. And this term corresponds to a superscript I minus 1 of z. Okay? And now it's quite straightforward. Minus ki is minus ki. Minus ki here. Minus ki here. And minus KIT. So you see the kind of the correspondence. And then finally, this Z inverse times B of I minus 1 corresponds to exactly this term. Let me just say this corresponds to Z inverse B I minus 1 Z. As you see, the order is reversed right here. Okay, so here, is that making sense at all? No? Any question? Can you see the correspondence? Can you see the correspondence that this equation, this very concise equation, actually is equation exactly what equation A1 and 1A is doing. Exactly the same thing. But here we are using the property already. We're using the property already because here B of Z is replaced by A of Z in reverse. Right? B of Z is replaced by A of Z in reverse. So this is exactly, actually the entire equation is nothing but equation 1A. Okay? So for this expression, we just don't have to keep track of B of Z explicitly. 不用那么明显的去记录 B of Z. We don't have to keep track of B of Z explicitly because we know that all the way along this algorithm, B of Z is just exactly going to be time reversal of A of Z. And now we are just rewriting A of Z as using Greek-related alpha. And keeping the structure. So here, let me just point out the I, in here we still have the same double loop. The same double loop, the I is basically, I is the how many units from the left. The number of units from the left. And naturally, we want to proceed from 1, 2, 3, all the way to the nth unit from the left. And J can be thought of as the time sample. J is the time index. If I is the unit, number of units, and what should I say the unit index? If I is the tells you how many units from the left, and J is simply a time index. Okay, so in the end, we have J being the time index, I being the unit number. Okay? After all, I'm using the same notation, I being the unit number, J being the time index. And there's a minus signs here and there, it's not super important. Okay? But interestingly, another thing to note is that we also have this one final line. For each I, we can use this formula to figure out its time, the sample value for J equals to 1, 2, 3, all the way to I minus 1. But I of these should be, there should be one last sample you need to append. Okay? In this for loop, J index runs all the way until I minus 1. You still have to figure out what is A supersede I subscript I. Okay, so this one final thing is going to be Ki. Alright? Why? Why? Because of this. Because one last sample, okay, corresponds to the path that has the longest delay. So this final line is a result of our observation at the beginning. Okay, so I'm going to pause a little bit. Any question? Is it making sense? Do you feel comfortable that you may be able to get it? Just go home and study it for a bit more. Okay? it's not that hard. But anyway, you need to, as an engineer, you need to convince yourself that all the negative sign, plus sign, all the notations are correct. If you spot any error, please let me know. Okay, it's time to take a look. We'll come back to this algorithm, and because this algorithm is kind of nice, because if you really understand the algorithm, then it becomes natural to do the reverse, to do the inverse. So now I'm describing the task. Our main task for today is to try to figure out the impulse response given the lattice coefficients. And as I told you earlier, that it's harder to do the inverse, solve the inverse problem. That is to say, it's harder to find out the lattice coefficients given an impulse response. That should be harder. But now I'm going to, this is a preview. Next time, we're going to try to do the inverse. Okay? What if we are given the impulse response? Then we find the lattice coefficients so we can implement the filter in this topology. Okay? So that's, we'll come to that next time. But before we end today's lecture, I would like to share with you then how we should be curious. Why is this relation hold? Why this nice, very nice, mysterious time reversal relation hold? Any comment? Any insight? Does anybody have any insight? Or does anybody want to suggest how we might be able to prove this relation? By what method? By something that we all learned in high school. 5 words. 数学归纳法。Mathematical induction. Okay, 2 words in English. I'm going to share with you, okay? So we are going to end today's lecture by showing that we can actually prove this. It's not that hard. Because this is a relation for every I. Okay, for every I equals to 1, 2, 3 to n. They should all hold. Right? So we know that A and B can be expressed in terms of A and B in the previous block. Right? So it's kind of natural if this relation holds for right here, and we should manage to prove that it also holds, the same property holds for the next block. If we can show that by mathematical induction, we can only come up with the proof. Okay? So this is what I'm going to show you next. Checking on that property. Checking on the property that B I Z is exactly Z to the minus IA of 1 minus 1 over Z. So check. Alright, we're going to do the checking by mathematical induction. So the first thing we need to check is that the relation holds for I equals to 0. Right? So for I equals to 0, we know that both A0 of Z and B0 of Z is simply x of Z. I'm simply, just simply 1. Because we're going to calculate the impulse response, right? The impulse response at the location of impulse to the impulse itself. So for I equals to 0, the relation holds. A and both A0 and B0 is exactly the Euler function. So the relation holds. Or should I plot it into Z to the minus 0th power, A to the 1 is Z. This is 1, and this is also 1. 1 and 1 is 1. Everything's 1. Okay? So this is a very straightforward thing to check and to convince yourself that for I equal to 0, the relation holds, right? So now, secondly, so let's assume that the relation holds for I minus 1. Assume that the relation holds, the property is true for I minus 1. And now for the next, for I superscript I of z, let's use the equation 1b. Okay? Let's use the equation 1b first. Now I'm going to use equation 1b. My equation 1b here is copy it. What to copy it is so the minus. I'm just copying that equation. Okay, and what's next? And we know that we have assumed that the relation holds for previously. Okay, so we are going to replace that part by, I'm going to just copy this part for now, plus z inverse times z to the minus I minus 1 power a of 1 divided by z. By the way, this should be I minus 1. Superscript I minus 1. And we're going to leave it there for now. Now how about this part? How about that part? Actually, we can use this, basically using the same relation. Right? You can use the same relation the second time. So it's still minus ki right here. But this part, let me actually say, since this describes a time reversal symmetry, so if we, I'm just going to quickly say, if we replace letter B here by A, letter A there by B, it is going to be true. Right? Because here A and B are this symmetry here. Time reversal symmetry. So we are going to, I can just easily replace letter B by A, letter A by B. Okay? So and that gives us a suggestion to replace A, so superscript I minus 1. We can express it in terms of B. Okay? So this is going to be Z to the minus I minus 1. Now B of I minus 1. 1 over Z. Plus, let's simplify this a little bit. So these are the inverse, these are the so many power. We have Z to the minus I power, A I minus 1, taking the value at 1 over Z. Okay, blocking the thing. Alright, we are almost done. Okay? So now Let's just continue. How do we get? 差不多可以凑答案。Because we want to show in the end that they equal to z to the minus I power a of superscript I 1 over z, right? Okay, so backtrack. Let's do backtracking. Z to the minus I power, then what is a superscript I of something? A superscript I of something, we can again use equation 1a. Equation 1a. So we again use equation 1a from here. Minus I, a superscript I there to the a superscript I minus 1. Remember that our argument is 1 over z. And do we have the same result? This is the question. Z I minus 1 times z inverse 1 over z times z inverse times minus k I. So do we happen to have the same result? And the answer hopefully is true. But is it true? Is it true? Okay, let's just move on further, all right? So this thing is already here. It's getting clearer. I hope it's getting clearer. This thing is right here. And this thing here is right here. Okay? And and actually there's a bracket. I forgot the bracket. All right. So hopefully, and this term here, so this is all very straightforward, right? You just need to be careful. That's z itself. The z times z to the minus I power is hopefully is going to be, so now we have z to the minus I minus 1 power and b of I minus 1 unit, 1 over z is already occurring, minus ki. So this term comes out. And how about the other term? The other term there is just exactly that. All right, so miraculously, we have completed our check on the property that it also will hold, given that it holds for I minus 1, it also holds for I. So that completes our kind of checking, right? So we can use an equation 1a repeatedly, 3 times exact. Oh yeah, so now that completes our checking. So indeed, this is a property that we hold. This is the time reversal symmetry we can prove by mathematical reduction. All right, so I need to hurry, and thank you for listening. I'll see you next time we continue to talk about the inverse problem.